morning, everyone. Welcome to the Smartwatergrid International Conference 2021. I'm Do Jang from Incheon National University. We are so pleased to see all of you attending this year's conference. This session's title is the Korea-EU Educational Cooperation Program. And we have the 5 speakers, and they already joined the educational cooperation program, and they received the degree from the International University. And today they will introduce their research and their thesis. And because of the some communication and some programs, we have the 3 speakers, the Ama Majae and Carlos Bariano and Kevis from Polytechnic Sofia. And all of them, they placed their video presentation, and I will arrange this session today. So first presentation is from Ama Majae and from Polytechnic Sofia. The research title is the application of the 2D the SWE covered model to Red River in Italy.
In water engineering, and also a freshly graduated from International University in Master of Civil and Environmental Engineering. I will present to you a study which is concerning the modeling of solvents in gases, which is something that can help both flow simulation and flow simulation softwares. So my presentation will be mainly on the context and how this implementation of better conversion models in this software can improve the simulations. I will show you how I did this, which equations I used, and how I worked in the software. And then I will show you some study case how these reactions, some study cases are replacing some context. The modeling of culverts, so culvert pipe or box pipe that will have the water conveyed from the upstream to the downstream of the bridge, train tracks, walkway. Whatever will keep the water from flowing, we need a culvert to let the river water pass over. And in 2D shallow water equation softwares, the issue is that you cannot implement the structure RR because they are 3D structures, and you need to find a way to implement them to correct water load and discharge simulation to have the best flow simulation possible. As you can see on the left, it's this flow simulation. A region next to this, and it's an issue that you can find from given issue, which is a flow parameter. So, the method actually currently used to model culverts in most softwares, there are 3 methods that are used. The first one is the most simple, simply keep a closed topography. When the topography is obtained from satellite or other methods, usually the bridge will appear as down, so the water will not pass there because the river will be cut. And we can keep the topography as it is, but it can provide some problems, like overstating the upstream water depth and understating the downstream water depth. And in general, it's not as good an idea, especially if most of the water passes through this bridge. We need to adapt at least the topography. This is the second method. We can locally plot the topography as you see here. The bridge was replaced with lower height, so the water can still flow. The problem is that a culvert is not acting exactly like on the channel, because there is some pressure there, so the water is sometimes making the culvert full, and the equation used to solve this are different than the equation used for shallow water equations. So you can have the effect of overstating downstream water depth and understating downstream water depth. Lastly, we can choose to implement a proper structure model in order to approximate the discharge that will pass from the upstream to the downstream of the culvert with equations that are related to the real behavior of the culvert. So this is a picture of a real culvert in the territory of Phoenix under the highway, and you can see that the water is really low level. It can act as a surface flow because water will pass with not much trouble. But in some cases where there is high hydrodynamic defense, you can see that the water rises, and the effect of this structure will be more, and it will slow down the water height will be greater in the upstream port, and that's why in the software we choose to remove the topography working sometimes to give you results that are a bit unrealistic. So this is an extreme example in the United States, where you see the culvert is completely full and the water will have lots of trouble to pass through the culvert. Sometimes there will be some overtopping, and it's important to know all of these phenomena in order to have those condition results. So this is the basic model of culvert that I use for my study. So you can see there is a culvert, upstream water height, downstream water height, some kind of slope inside. The culvert will have a shape, the diameter, and of course, sometimes the height from the entrance and the exit of the culvert is not constant. So we need to take all of this into account to calculate what will be the discharge and the culvert each step. And I used rectangular fluid in Paris to also make some experiments, have some data to verify the results. So I had my own model that I could play with and take some data to verify that the suspected equation data. So on the software that I used to model Spaceless is a software which is open source, so that anyone can use it and modify the source code. And it's for all of the fluid mechanics equations, not only shower water equations, it can be for two phases, it can be for gas, it can be for multiple kind of equations, and it has some particularities similar to other softwares. First, you can solve this equation, but not only explicitly or B2B. And also, it has an artisan grid, which can really help for really fast computation with the partition grid. At each time step, the grid will adapt in order to model with higher accuracy in the place where there is lots of events happening, and not use a too fine grid in the place where the water level will be constant. And as for before my study, we didn't have a working over models, and that was the point of my study. So we're doing the behavior of overs in order to perform simulations. And I use Python first to verify my code, and then I use Basilisk into to verify its solid state. So about the method I chose was upstream and downstream source method. So I can see that the code here, and we will have some cells upstream and some cells downstream that the user will have to choose. And when you specify the cells in all the culverts geometrical parameters, you can obtain an each the water height in the upstream part and the water height in the downstream part, and the link water height is an equation to obtain the discharge. And the water will be taken in this area to correspond to the discharge, and to be introduced in this area to release that discharge. And this is the method behind the upstream downstream coupling. One of the main problematic switch equations that we use to link the water height here and here to discharge. So some studies show that there is some culvert flow classification, and for each culvert flows, we will have a different set of equations. So I choose to use 6 different culvert flow, depending on the upstream, downstream water height, and also the characteristics of the culverts. So at each time step, the software will calculate in which class we are. So let's say we're gravity flow inlet, and it will help to choose the equation. And from this equation, we will calculate the discharge from the upstream water height, and then the software will do the rest to solve everywhere else to the shallow water equations. So to evaluate this model that I just presented to you, there was some study case. First one is a very simple gate without all the equations that I just showed you. It's a simple equation for all the water heights, but just to verify that the source dam coupling works with this simple case. So we have the discharge system to the water height upstream and downstream, and I verify that it respects the analytic equation. Sorry, and you can see that the module, the basic software has higher accuracy, simple problem. Then we choose to use the laboratory data that I obtained, and so I changed the discharge every time, and I observed the water height upstream, the water height downstream, gave me lots of data, and then I used the simulation software to verify that from the
Thank you for the presentation from G. He conducts the covered modeling using the 2D SW model, and he applied to a real area from the Red River. So, based on his research, map 3D simulation are important to the hydrological and hydraulic simulation. And about the hydraulic structure, it is very difficult to present the some of the flood condition and some normal condition of the your case, but more the improved the approach to numerical simulation can conduct the some other set of the real phenomenon and flood simulation. Thank you for the presentation, and now we want to move the second presenter, the Carlos Fabiano from Polytechnic University of Catalonia. The presentation title is the study on alternatives for the renewal of the water transmission in pedestrian in Spain.
Hi, my name is Carlos Fabiano, and I'm going to present you my thesis that I wrote in Quito International University. I'm going to share my screen, and I'm going to show you. I'm going to show you my PPT. So I wrote the title of my thesis is a study of alternatives for the renewal of the artery of Pastoral. Pastoral, this is an artery that goes from a town in northern Catalonia to Barcelona. So it sends water to the main city, to the capital. This thesis is divided by 8 points. The first one is the introduction, and I will explain the main points to start everything, to understand. Then I'm going to talk about the objectives, then about the current situation, what's going on now, what's happening. Then I'm going to talk about design flows. In the 5th point, I'm going to explain the study of the corridors and the different alternatives and the hydraulics related. The 6th point is about the construction method. And the 7th is alternatives study. And then we will talk about the conclusions. And the conclusions are made for not just for this particular case, but also for other cases that might be very similar. So, about the introduction, the artery that feeds the entire drinking time is a river, a very important river in Catalonia. Catalonia is a region in Spain. And the Ter is a very important river that feeds Barcelona's water. So this artery that feeds the entire drinking water treatment plant from the dam of the Pastoral, as I said, and it does it during the whole year. The maintenance of the artery during this process is useful. It has a useful life, has been very limited. And now it's time to change it because the concrete is very damaged and so on. And this artery is a basic supply for the metropolitan area of Barcelona. So it's a very important infrastructure for the country. The objectives of this thesis are summed up in 2 points. The first one is to analyze and study different alternatives. And the second one is splitting the existing hydraulic artery into Barcelona and the Pastoral. So first of all, we're going to have different alternatives. And second of all, we're going to split this artery in different ways. The current situation, this artery was built in 1966. In this period, it was a boom. It was a very high and quickly expansion in Spain for infrastructures. It was a gold age for Spain, talking in infrastructures, obviously. And after all this time, it has suffered some damages. The discharge of the site is 8 meters square per second, the level difference of the difference is from 189 to 184, so it's very low. There is almost no difference. And the white inlet channel, it's a white inlet channel, and the circular section is 3.05 meters diameter. Well, I have to say that the level difference is not till Barcelona, is to ETAP, it's infrastructure before they collects the water to send after that to Barcelona. But this segment has a better conservation level. So the design flows, as you can see in these tables, you can see how the design flows has been disclosed from 0 to 95 minutes. Distribution of treated flow expansion time period from 2004 to 2018, and then you have the last ones, because this study was made till 2018. So this is a huge change, and we can see how the design flow has been reduced in the main peaks. If you compare the both columns, you can see that are reduced. For example, the 10% of the time is lower than in these last years than now, than the time where it was made. And then we can see the evolution of the time over the years that exceed the 6 meters square, that 6 cubic meters per second. That exceed the number 6. So you can see a reduction of the time, and now is not almost zero, but barely. So it has changed a lot. Maybe in 20 years, it has changed a lot. So the future trend is to reduce flow from the tap in order to allow more flow circulating along the river. So now the government is interested that the river has to have more capacity itself and doesn't have to distribute that much to the people. You have to find new sources for that. So taking that into consideration, you have to find a new circular or a new pipe. So the study of the corridors have 4 points. The first one is we have to capture in the existing pipeline. So we have to capture water in making the same point in the existing pipeline, and then we have to design a tunnel corridor and taking into consideration that we already have 2 corridors, one for the high-speed railroad, AB, and another for the AB7 is the motorway corridor. We have to try to take profit of that and use these existing infrastructure corridors. Another point is like the design flow has to be 6 cubic meters per second, but as a peak, as a match, not as a mean value. The second is like the length of the driving. We have to take that into consideration. How long it is. We have to take into consideration that probably we are going to use reinforced concrete with sheet metal jacket because probably this is the best one. Because we already have other studies. It's not just that, it's on technology and it's also on the cost of the meter square. And for the transport of the flows of the design, we contemplate 2 main alternatives. First one, driving by gravity or free sheet. And the other alternative is pressure conduction. Okay, so here we can see the main parameter, the discharge. Okay, is 6. Okay, is 6, and then the diameter is 2.8, and then we can see the other values. Here we have the driving by gravity free sheet, and we can see how we have worked. The same for pressure conduction, and then the construction methods. Well, we have different methods. The first one is the tunnel with push tube. So we can see here the scheme and the different sketches. The second one is the tunnel using EPV. And then the third one is the tunnel using DBM. Well, there are a lot of factors that determine that. But the main one, when we have that technology and knowing that who has to pay that is the government, probably the most important point is not the technology, sadly. Probably is the money that the government wants to pay for that. And then taking a look at the alternatives, we have considered 5. The alternative 1A is the current layout with free sheet operation. Alternative 2A is a high-speed road, railroad high-speed road, with natural pressure, final pressure section. And then alternative 2B with natural pressure but gravity final stretch. Alternative 3A with final pressure section. And alternative 3B with pumping and gravity final stretch. All of them are following the railroad. And as a summary, we have all the points here. So going to the conclusions, first of all, if we see the budget, we see that the first alternative is the most expensive one. The first alternative consider the current layout with free sheet operation, and the cheapest one is the last one, the 3B. This one is the pumping for using the core rail with the train, pumping, and also with the final and the gravity final stretch. So pumping is good in economic terms. Okay, taking into consideration the first point. So going to the conclusions, we can see that 5 years ago, the flow was 6 cubic meters per second, and exceeded just 28% of the time, while during the 2017 and 2018, it has exceeded only 18%. I said before almost 5 or something like that. I'm sorry, was that? And the alternative route chosen as the most viable solution is the so-called AVE, that is in the railroad high speed that we have in Spain. We didn't consider the AB7 because it has a high environmental impact. The material chosen was the prestressed concrete with metal jacket sheet. It's very resistant, and this prestressed concrete is good because, first of all, we have to build a long pipe, and it's much better to do it prestressed. Also because of the pressures that it has to save. It has to save all the length. And also with the metal jacket sheet that helps to confine the pipe. The fourth point is a conventional tunnel rolled out, and a hydraulic one chosen. And pumping is rolled out due to the energy cost in the future. So at the end, we didn't consider pumping because of even though at the end is so cheap, in the very beginning is so cheap, at the end, in the long term way, talking, it's expensive because maintenance has to be very expensive. So the alternative 2B is chosen. An alternative 2B with following the railroad with natural pressure and gravity final stretch. So at the end, we don't need pumping, and gravity really works by itself. This is the conclusion that we have started for this thesis, but at the end it works for everything. Talking especially when we are talking about long meters. First of all, if we want to design a new pipe, we have to find new infrastructures. Second of all, we have to find infrastructure that already existed because it's easier for it to build. And then pumping is expensive, talking in a long-term way. As a material, for other projects will be the processed concrete with metal jacket due to the resistance. And very important, we have to really see, we have to watch how the discharge is. We have to study the historic data, and then we have to decide. We can't miss that. And that's all. And thank you very much. And I hope you have enjoyed this presentation. Thank you.
Thank you very much for a nice presentation. From the Carlos Mariano, he researched about the water supply system, the transmission line for oil field and oil specialty. And for the improvement of the transmission line, he suggests some optimal material and optimal pipe route and some consideration of the economy and some pumping and some natural water supply. So he suggests some optimal methods, consideration of the economy, and he suggests methods can apply to the real system. So by this, some valuable research for real area. So I hope to considerations of this research outcomes and applies to real system. Thank you. And for the next presenter is the Kevis, the Boinski from Polytechnic Sofia. His the research title is quantifying the climate change hydrological impact using GI2M rainfall runoff model. The case of the Raylan watershed impact.
Good morning, everyone. Hope you all doing fine amid this pandemic, and that you settling in properly in this Smart Water Grid Conference, National Conference of 2021 edition. So my subject will tackle the quantification of climate change hydrological impacts using GI2M rainfall runoff model, and I'm going to apply this study on the Raylan watershed, which is in the south of France. So here's the plan. We'll start with the introduction. So climate variation influences watershed hydrological behavior due to its correlation with precipitation and temperature, and impact river stream flow directly. As you can see here in the water cycle, everything is connected. Therefore, climate change is one of mankind's biggest challenge. Indeed, human beings have been experiencing temperatures and rainfall variation as an increase in extreme weather events may have been observed over the past 30 to 40 years in most part of the globe. As you might know, water is an essential element in human society, sustainability and development. Indeed, it's directly linked with the electricity production, the agricultural and clean water supply. And there's going to be an increase in socioeconomic water demand. All of this equilibrium is threatened by the uncertainties caused by climate change. Okay, so let's give some numbers. Under current conditions and practices, the world will face a 40% shortage between forecasted demand and available supply by 2030. Plus the projection estimates the world population to top 9 billion people by 2050. Therefore, feeding such a population with current technologies will require a 60% increase in agricultural production, which consumes 70% of today's water resources, and a 50% increase in water withdrawal, according to the World Bank. However, water scarcity is already a challenge for most countries. Now they need to take the increased demand as a critical factor for water management. Precisely in 2017, researchers have estimated that 30% of the world population live in water scarce areas, and approximately a quarter of the world's GDP is exposed to this challenge. Therefore, assessing rivers, stream flow, future variation information is critical, especially in integrated water resource management and hydraulic infrastructure designing. So this study focused on establishing a framework for future discharge assessments under climate change conditions. Now, let's dive into the model. GR2M is a conceptual model developed in R by Professor Mori in 2003. It's a monthly water balance governed by two parameters, which is why we call it GR2M. It presents a lot of advantages. It only requires three data sets: precipitation, temperature, and discharge, in order to perform relevant hydrological simulation and processes. It was developed in R software, so it's a fast computation and intuitive and resourceful. Besides, the model performance is included within the R framework using the Nash-Cliff criteria, which can present a lot of advantages when you try to assess model quality and relevance. So, in a nutshell, GR2M consists of a production reservoir governing the production function, and is characterized by its maximum capacity, and a gravity water reservoir that governs the transfer function. So the first parameter, x1, represents the maximum capacity of the storage tank. The second parameter, x2, represents the groundwater exchange coefficient parameter at a gravity water level. So here you can read all the equations, and you can come to it maybe later if you need more questions. So now let's talk about the study area and present all the data. So the watershed is the main unit for hydrological modeling. Therefore, climatic data are needed on the watershed level in order to infer hydrological behavior on a coastal level. So conceptual hydrological models or precipitation runoff model that are built based on observed empirical relationships among different hydrological variables. So they are really different from a black box model, which consider precipitation runoff relationship only statistically, but they are also different from the physical-based distributed hydrological models, which are based in solving a differential equation describing the physical law of mass, energy, and momentum conservation. So the conceptual model used requires four hydroclimatic data, naming the rainfall, the temperature, the evapotranspiration, and the streamflow. Evapotranspiration can be inferred from the temperature, as we'll see in the next. So the watershed has been chosen for the study case. This 73 km square watershed is located in the south of France and have the advantage of being go through three weather stations closely located nearby the watershed itself. So they are hydrological regimes, Mediterranean pluvial. Therefore, is characterized by a single annual alteration of high and low, whereas you can see in the graph on the right side, the rainfall watershed is mainly fed by rainfall. So here is the map of the three stations nearby the rainfall watershed. So here is some detailed results. So after performing a spatial interpolation, we can see that there is not much difference when you use the Thiessen-Pflüger method and the arithmetical mean method regarding the precipitation data. However, you can see that Thiessen approximation tends to top the arithmetical approximation, as Tourette has a bigger influence than the other rainfall station, and the rainfall at Tourette station is bigger than the other ones, as Tourette is located nearby mountains, whereas the other two are located by the sea. So now, when it comes to the temperature series, I had to fill in the gaps that I had in the temperature series by using a linear model interpolation between two stations, namely Fréjus and Tourette. I didn't use for Saint Raphael, as the influence was really low, 5%, so it was not necessary to add the station. Now we can see that when we compare the arithmetical method and the Thiessen method, we see that the Thiessen method estimates the temperature lower than the arithmetical mean. This is because Tourette is nearby mountains, so the temperature is lower than by the sea, as Fréjus, for instance. Now the last parameter to have before starting the simulation is the potential evapotranspiration. It's a critical parameter for the hydrological cycle. However, representing the evaporative demand can be problematic when creating the hydrological model. PET, potential evapotranspiration is mainly an agronomic concept that lacks a clear definition at the catchment and regional scale. So the literature contains a wealth of PET models with different data. However, for our purposes, we are going to use the format formulas and to use the model presented in R software using the same formula and averaging temperature data sets, which is the PE of the. So now let's talk about the results and some discussions. Now we can start the simulation. So basically we have data from 1980 to 2010, okay? We divide this period into two sets, one for the calibration and one for the validation. So the calibration parameters were used as inputs for the validation parameters, which gave us, after 9 screenings, an NSE of 0.798, which is an excellent performance for the model. And now these two sets of parameters, X1 and X2, are the one that best characterize this watershed and can be used to inform discharge, future discharge variation. Now, what we need to do is to obtain the hydrodynamic variation for simulating and inferring future discharge variation. So how do we do it now? What I need to do now is to obtain the monthly average changes in specific hydrodynamic data. So in order to have them, I used a general situation weather forecast on the watershed, comparing the 1995 to 2005 climate with 2025 to 2020 climate from previous PhD researchers, and I implemented those changes in the GR2M model with the set of parameters that we know who best describe the behavior of this watershed. You can see the samples of the monthly average changes, and here in the table here in this table here. So now, after implementing this new set of changes, I obtained this specific graph comparing the future and present discharge from the results of the GR2M model. And as we can see, the two graphs are similar. However, the peak of the future flow is higher than the one from the present flow, especially here in September. In conclusion, GR2M is a powerful and resilient model, giving us excellent results with the NSE of 0.78. Combining the coupling the GR2M results with general circulation model, which basically used as water forecasting for the IPCC, for example, can help infer the hydrological behavior of watershed. So the watershed future discharge is very similar to the present one, except during peak events, as we saw before. However, there's a lot of improvements that can be made. For example, we can reproduce this method on different gulf watersheds in France or elsewhere. And we also need to talk about the ungulch watershed case. We can use, for example, remote sensing data as input for the GR2M in order to inform some discharge variation for the ungulch watershed. Here are some references. Thank you very much for Dongwoo Chang, who was my professor at the International University. And thank you to everyone who listened to this presentation. I wish you a very good day.
Thank you very much from Kevin. Kelly's University. His research is concentrated on the water balance using the GR2M model, and for the hydrological analysis and promote the make the hydrograph using the hydrologic process. It is important to use some temperature and some characteristics of the soil and basin, and so he suggests the hydrograph for using the monthly data in real area, and he applies the model calibration and validation to his build model, and he compared with the current condition and the general circulation model from the climate change scenarios. So it is very interesting for his research, and maybe in this case we can suggest that the hydrological process and their analysis is very important to model accuracy. So some calibrated model can apply to the real system, and for the current condition and for the future condition, we can compare together and we can estimate the future some water resource management. So it is maybe you can apply to the real system, and these research outcomes can apply to and expand to the near place of the study area. Thank you very much for the next presentation from Kelly. And the three of the speakers' presentation is played by the videos. So if any question from the floor, we can apply to we can ask to the speakers by email or some online communication. So I hope to if you have any suggestion and comment and question, please send to us and we can connect to the speakers. So now I want to close the session. We have just to remain the speakers, but because of some technical problems, we can't connect it to the speakers. So maybe we can have the meet again for the next conference of the smart water education. And so thank you for the participation of all participants, and I want to close the Korea EU Educational Cooperation Program, and I hope to meet again for the next FWGS. Thank you.